If there are no questions, we're just going to jump right into the material. Chapter 1 is a lot of review and then some. And so let's take a look at the topics in Chapter 1. One, the scientific method. There's no like one-size-fits-all scientific method, but I'll tell you what I did, and everybody else that worked around me did day to day. Some scientific discoveries are just made serendipitously, just by chance. But if you're working, going into the lab in the morning and it's working, you know what you do with scientists? Most scientists, what chemists do, chemists study matter, the properties of matter. In fact, when we're thinking about this is our, ultimately we want to know the properties. The properties would be like the physical and chemical properties of the substance. But to get better insight into the properties of matter, what do you want to know about the matter? Like gold. Gold behaves differently than silver. It behaves differently than helium. So what do you want to know about matter? Or how do we study it? Well, one of the things we do is we try to correlate it with things. So the properties are going to be correlated with two things. We correlate the properties with the composition. The composition of gold is different than the composition of silver. Well, what is the composition? The composition, because what is it made out of? Gold's made out of protons, neutrons, and electrons. Silver is made out of protons, neutrons, and electrons. So why do they behave differently? They're made up of the same thing. Well, they could be made up of the same thing, but how they're structured could be different. And so there are lots of examples of this, like carbon, the element carbon. The element carbon forms diamonds. Diamonds are made out of pure carbon, but what about graphite? Do you know what graphite's made out of? Pure carbon also. In fact, I just bought some 99.99% pure graphite. It was cheap on Amazon. But graphite and diamond have different structures. So this is what we do, and how do we study these types of things? Because we want to understand the properties more. That way we can predict things, predict how things are going to react or how things are going to behave. That's always a nice thing to do. And sometimes these predictions are very difficult to do. And especially as the systems become more and more complex. In physics, you spend a lot of time, because I took quite a few physics classes, you spend a lot of time looking at the hydrogen atom. In fact, I have a 2-volume book. This 2-volume book, volume 1 is over 1,000 pages, volume 2 is about 600 pages on the hydrogen atom. So, yeah. But as things get more and more complex, they become more and more difficult to predict. Like biological systems are very difficult to predict sometimes. Certain things, yeah, you can make predictions. But what we want to do is we want to understand the properties in this correlation. So if we think about the scientific method, different classes will have different steps here, but these are the typical steps that I did. And the scientific method, step 1, what all scientists do. All scientists take observations. If you ask what a scientist does, they observe nature, how it behaves, those types of things. And so we want to take observations. And then what we do is we look for patterns and trends. Okay. And if these patterns and trends are consistent, precise, then we can come up with a law, a scientific law.
Would it be theory would be?
Theory and the law aren't the same thing. Yeah, a law is just a typical law. Let me tell you a typical law. There are 2 ways we can get laws. One way is from the observations and modeling the patterns. And so this is called empirical. And so we have empirical laws, which are based on empirical equations. Empirical, do you know what empirical means?
Measure.
Yeah, measured or observed. And so these are laws that are based on observation. So for example, an apple falls from the tree. And there's a pattern to that. How long does it take? How fast is it going when it strikes? Etc. And those can be put into mathematical equations. Those mathematical equations are called empirical equations, mathematical equations based on the observations, and those are the laws. Or we have theoretical laws. And so we have empirical or theoretical. Theoretical approaches things differently because, typically you'd have to know the theory. Now, what is a theory? Well, from a law, we go to a hypothesis. A hypothesis, this is digging deeper into the law, And so, for example, an apple falls from the tree, so we can come up with an equation. How long does it take for the apple to hit the ground? The distance. And so we have an equation like that. But then you want to dig deeper. Why is the apple falling down? Why isn't it falling up? And so you dig deeper into that, and you get into, well, this would be the laws of gravity, or the law of gravity, whatever, gravity, right? There's something that's pulling it to the center of the earth. And then you come up with a hypothesis. Well, there's something called gravity. And then eventually that becomes refined into a theory. Do you know what the theory underlying gravity is? The theory underlying gravity?
Gravitons?
Maybe gravitons are part of the theory, but the theory has a name. What is it?
I don't know what the name would be, but it would be inertia.
Inertia? Well, actually, let me just make a long story short. The theory is called the theory of general relativity. That's the theory underlying gravity. And so, did somebody just come up with a theory of general relativity? And then, no, it went through all these steps. Eventually, somebody refined it to the theory of general relativity. There's theory of special relativity. I'm sorry? Oh, hypothesis. Hypothesis precedes a theory. Hypothesis is what we call a tentative theory. A tentative theory hasn't been widely adopted yet. When you get to a theory, we have, so this is tentative, what we call tentative fundamental explanation of why the apple falls to the ground. And so things start off as a hypothesis, and then we get to a theory which is an accepted by, I don't know if there's a certain limit, or what, but eventually it becomes widely accepted. But a theory should do two things. It should be an accepted fundamental description of what's happening. Okay, so it's a fundamental description of what's happening with the apple falling to the ground. So there's some kind of deep, these things, the space-time field or web or whatever. You can get into it. We're not. Accepted fundamental description. But the theory should do two things. One, it should be widely accepted, not tentatively accepted. And so in order to become widely accepted, it has to be tested. People are going to try to debunk the theory. Everybody tries to debunk the theory. You'll see these on YouTube, like perpetual motion machines, with people trying to debunk those and people trying to support those. And so it's going to go through that science. There's no scientific police. Science is a self-policing. And one of the things is people try to debunk theories. Two, do you know what else a theory should do? Yeah, good. The theory should predict new unforeseen results. New results. Results would be observations that have never been seen before, but the theory would predict these observations should be observed. And so like the Higgs particle. Have you heard of the Higgs particle? The theory predicted. I'm sorry?
The Higgs boson?
Yeah, the Higgs boson, etc. those things come from the theory. So the theory predicted this, and then people went out and looked for it. And if they observe it, well, that's a new result. And that new result reinforces the acceptance of that theory. Now, theory and hypothesis, these get mixed up sometimes. Like for example, in like criminology, you have a theory of who murdered that person, and whatnot. But maybe that's more of a hypothesis. You have a hypothesis of this.
What would be the law? Someone died? Someone murdered?
No, law is somebody died.
Yeah.
That's it. A law is just it's a factual observation. It doesn't get into who killed it, the motives, this kind of stuff. The theory goes beyond. There. And so we could do something very simple quickly. Like for example, we're looking at measurements. And one of the things we measure is temperature. So we measure temperature. One of the observations would be like this. If I look at let's look at the Fahrenheit temperature, the temperature in degrees Fahrenheit and the temperature in degrees Celsius, and then just take some observations. You probably have these memorized. So, for example, if the temperature were exactly 32 degrees Fahrenheit, do you know what the Celsius temperature is? 0. This is what we call the freezing point of water. So that would be 0 degrees Fahrenheit. 32 degrees Fahrenheit is equivalent to 0 degrees Celsius. This is exact. So I'll draw. The exact means that these have infinite precision. It's not about 32. No, it's exactly 32. And it's not about 0, it's exactly 0. And so if we have that, we call these infinite sig figs. And so how many sig figs does 32 have? Not 2. You'd say 2 because but it's infinite because we know that's by definition. These are exact numbers. Does that make sense? And then this, it's not about 212 degrees Fahrenheit. It's exactly 212 degrees Fahrenheit is equivalent to exactly 100 degrees Celsius. And so both of these have infinite number of sig figs. And so these are observations here. We come up with a pattern. In science, we love to graph things to see if there's a pattern here. And there is a pattern. So if we go to 0 degrees C, then we're up at 32 degrees Fahrenheit. And if we're at 100 degrees C, we're at 212 degrees Fahrenheit here. And then we look, is this a linear pattern or non-linear pattern? And it turns out this is a linear pattern. We just need 3 points will define a curve, 2 points define a line. And so we take a third point and see it's linear. And then once we have it, then we can come up with a law. The law is just representing this pattern using an empirical equation. What would be the empirical equation for this? The empirical equation for this would be the temperature in degrees Fahrenheit, this is our y, is equal to m. Our slope is going to be what? Delta y, so that's going to be 212 minus 32 degrees Fahrenheit over delta x. Delta x is going to be 100 minus 0 degrees Celsius. And then plus the intercept. What's the intercept? 32 degrees Fahrenheit. And so, so we end up with this equation. Temperature in degrees Fahrenheit is equal to 9/5 degrees Fahrenheit over degrees Celsius plus 32 degrees Fahrenheit. Do you recognize this equation? This equation is often simplified. Degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. And so this is an example of an empirical equation, but it doesn't really tell you much beyond it. This is just an observed pattern. That's it. To go beyond that, then we'll come up with hypotheses and try to come up with some kind of theory. But oftentimes we don't need, do you really care what the hypothesis is for this? Or some theory? Do you want to hypothesize anything? No, we just want to use the equation. So oftentimes laws are very useful, like the ideal gas law. The ideal gas law is PV equals nRT. Right? We can use that, but do you understand it beyond that? Do you understand this at a deeper, more fundamental level? Probably not, but in this class, you're supposed to understand it at a deeper level because we're going to get into kinetic molecular theory. And we can derive this law based on patterns. The patterns were, do you remember the simple gas laws? Charles' law, Boyle's law. You don't have to remember those, actually. I'm not going to test them. And those are just observations, but we can also derive the ideal gas law theoretically. And so if we go to kinetic molecular theory, we'll get the exact same equation that we got from observations, looking at Charles Boyle's law, but from a different perspective. And so this is why in science we do a two-pronged approach. We try to do as much stuff theoretically. The more stuff we can do theoretically, the less we have to memorize. And so if you can figure out all the laws based on theory, okay, give me some more laws. If you can figure out all these based on theory, that's good because all you have to do is know the theory, then you can derive everything else. You can derive all the observations from theory just working backwards here. So ultimately, this is what we want. We want a good theory. This is why, like the theory of general relativity, it makes great predictions for space, time, whatever. And so we want a good theory that we can use to predict, but the theory becomes too complex. Do you know what is the theory underlying chemistry? Do you know what the theory of chemistry is? It's called? Quantum mechanics, yeah. That's the theory. And quantum mechanics, to make the predictions, the math is horrendous. And so making the predictions using quantum mechanics is very difficult. If you tried to predict everything in a biological cell using quantum mechanics, that's a horrendous task. Horrendous. And since it's so horrendous, you make simplifications. And when you make simplifications, those add to uncertainty. And the more uncertainty there is, the less precise your predictions are going to be. And so we try to do that. And so our two-pronged approach is we can't do everything theoretically. If we could do everything theoretically, there's nothing to memorize. You know the theory, you know it well, you can predict everything. But since we don't, we need two-pronged. We need to do things, and this is interesting. If you go, there are two camps of physicists at the Large Hadron Collider. You know what the two camps of physicists of the Large Hadron? This Large Hadron Collider is that super collider thing in Europe.
I thought it was in Germany.
Germany is part of Europe, I think. I mean, isn't it Switzerland?
I thought it was Germany. It was Holden.
Okay. Well, I think, yeah. Anyway, it's the Large Hadron Collider. The two camps of physicists are the experimental physicists and the theoretical. So you have the experimental physicists and the theoretical. Well, that's our two-pronged approach. We're going to do both. We're going to be the experimental and the theoretical. And so we're not going to distinguish. Are you experiment? Well, when you get to higher levels, you'll distinguish. But everybody's going to be doing both. The experimental are the observations. Observations. You take it's a lot of work. You take the observations, you look for patterns, that kind of stuff. You memorize certain things. And then we have the theoretical. And so our two-pronged approach is we want to approach things from knowing some observations and be able to predict these types of things. Like this, we know this observation, we can predict this equation. I don't have to memorize this equation, or you could memorize this equation if you want, but it's easy to derive. Or theoretical. You want to derive this equation using theory? Is that even worth it? Using, in other words, would this be easy to derive using quantum mechanics or no? So some things are just much easier just to memorize than to try to predict. Like, for example, do you know what the chlorine's color is? Do you want to try to predict that using electrons, excitations, and absorption, emission of light? It's probably to say, it's yellow, green. I memorized that. And so this is our two-pronged approach. So we try to minimize the amount of memorization and work, but sometimes it's unavoidable. and do that. So that's a scientific method. There are lots of examples of this. So normally we just do observation. Like, for example, when you get a PhD, you have to come up with some original. And you think, everything's already been done. What can you do that's new and original? Well, nothing has been. Everything requires so much work that there's so many unanswered questions out there. It's not that difficult to find, how, people don't really know how things. It would be nice if everybody knew, what exactly is going to happen, when things. But anyway, so this is the scientific method. We'll look at properties, classification, kind of together. So the classification, we have matter, which consists of the physical material of the universe. Matter has mass and occupies space. Although, with all this theoretical physics stuff, it's, what is mass? All these fields, it's pretty interesting. But for chemists, we're just looking at the physical material of the universe. When we look at the physical material of the universe, we can break it down into what? Solids, liquids, gases. What are the states of matter? Solids, liquids, gases. And there's a fourth state of matter. You know what the fourth state of matter is? Plasma. So examples of plasma would be like a flame or the sun. The sun is a giant fireball. It's plasma. These are LED, but the old fluorescent lamps were plasmas, neon lamps, etc. Those are all plasmas. So typically, if we take a solid, we heat it up, it melts into liquid. We take a liquid, heat it up, it vaporizes into gas. You take a gas and heat it up. When you heat up a gas, then the collisions become more and more violent. And there are different ways we can ionize matter. One way is blast it with ionizing radiation, gamma rays, X-rays, alpha particles, ionizing radiation. The other way of ionizing matter is just have high energy collision. You have a high energy collision, it knocks an electron off, you create ions. And so a plasma is an ionized gas. There are two types of plasmas. There's what we call the non-equilibrium plasma, or the low energy plasma, which is partially ionized gas, which would be like a fluorescent lamp or neon lamp. And then you have thermal plasmas or equilibrium plasmas, which would be like the sun, in which you have a high degree of ionization. Okay, once we have that, then we break it down into homogeneous versus heterogeneous matter. Homogeneous and heterogeneous, this is just to our naked eye typically. Because if we dig deeper and deeper, then we'll see all matter is kind of heterogeneous. It depends on the magnification level. So a homogeneous just means it's uniform, right? If it's uniform, does that mean it's pure? Or could it be a mixture? It could be a mixture. So either it's going to be pure. If our homogeneous matter is pure, that means it's a pure substance. Well, substances are pure nonetheless. And if it's a substance, we have two substances, which I asked you earlier. One is the element, and the other is the compound. So the compound water consists of hydrogen and oxygen, and we could break it into the elements by doing what? If I took a compound, we could break it into the elements the element hydrogen and the element oxygen by separating the hydrogen and oxygen. And we have two types of separation techniques. We have chemical separation and physical separation. Can you give me examples of physical separation? Distillation. Would distillation separate the hydrogen from the oxygen in water? No. Filtration is another common one. Can I filter out the hydrogen from the oxygen in water? No. Instead, I'm going to have to use chemical separation. Can you give me one example of a chemical separation technique?
Electrolysis.
Electrolysis, in fact. Good. In fact, that's commonly done. So you just pass an electric current through water, and you can get it to, what we say, electrolyze. If you have salt water, you can dump a 9-volt battery in there and it will electrolyze. I have a YouTube video I usually show. Maybe I'll show that sometime. If it's heterogeneous, then typically that means it's not pure. It must be a mixture. How can we tell? How can we tell, if it's a mixture or if it's pure? How you can tell are the properties. So, for example, elements and compounds, they both have variable properties or fixed properties, like water. The properties of water are always the same no matter where you get it. So it could be water from Mars or water on Earth, and as long as it's pure, it's going to be the same. However, do you think the water on Earth and the water on Mars is going to be pure? No, it's probably going to be a mixture. There's going to be probably minerals dissolved in there. Mixtures, are they going to have this exact same properties? So the mixture of water on Earth versus the mixture of water on Mars, that is the dissolved minerals in there, are going to be exactly the same, the exact same properties? No. And so in other words here, elements and compounds, both of these have fixed composition, fixed properties. So what are some common properties? Physical properties. Yeah, so one of the things is if somebody gave you a cup of colorless liquid like this and told you to drink it, would you drink it? No, you'd probably want to know what it is, right? And how would you, what are the things you could tell what this is? Well, one way you could tell is you could try boiling it. And so let's say this liquid boiled at 80 degrees. Would you drink it? No, absolutely not. If this liquid boiled at 150 degrees, would you drink it? No. If this liquid boiled at 100 degrees, would you drink it? I don't know. Maybe. What else boils at 100 degrees other than water? This is something you probably want to know. And then you want to know if this freezes. At what temperature does this freeze at? So if this boiled at 100 and froze at 0, would you drink it? I don't know. I still don't know if I drink it. Oh, that's a good point. Yeah, Celsius. Yeah, you probably want to do a lot. You know what I probably want to do? I'd probably just want to assume it's a mixture and then just try to purify it. And then I'll drink it. Because you don't know what's in there, right? And so probably if you just assume this is a mixture, how can we separate a mixture into the components? The components, this mixture could be comprised of elements, a mixture of elements and compounds. And so one of the things we could do is, let's say, this is water, but there's a little bit of mercury salts in here. And that little bit of mercury salts doesn't really change the boiling point that much or the freezing point that much, but you don't want to drink it. And so we'll just assume it's a mixture and then try to purify it by using what would be a good technique? Distillation. We could use physical separation techniques for this. Say chemical separation, physical separation. Or we know, mixtures have variable properties depending on the composition. And so mixtures have variable composition in variable properties. Sometimes mixtures are very hard to separate. I mean, this is a big challenge in science. How do you separate the mixture? And, not so easy. Sometimes it's easy. So that's a classification of properties of matter. Properties would be like boiling point, density. You know, how can you tell fool's gold from real gold? Probably the easiest way is density, because you know what real gold's density is? About? You know what the density of water is about? About 1 gram per milliliter. And the density of gold is, about 20. Good. The density of fool's gold is way less. It's like 2 point something. So there's a huge difference in density. So it's really easy to tell the difference between fool's gold. Actually, any geologist would be able to tell. Really easy. Fool's gold is not malleable. It's not ductile. You take a hammer, it's very brittle. So you don't even need to measure the density. Just take a hammer and try to break it apart. But they might not be happy. You're crushing their fool's gold. Density. What about chemical properties? No. Chemical properties, you might try to, before drinking anything, you might try to see if anything precipitates out. Chemical properties, we'll talk about these. We have physical properties, which are standard physical properties that physical properties often involve physical changes, like when you melt something, you go from frozen H2O to liquid H2O when you melt something. Solid to liquid. So it's still H2O. So its composition didn't change. Melting point, boiling point, density, etc. Color, form. Chemical properties, we're going to talk about these in more detail. The chemical properties are the chemical reactions. How many chemical reactions happen in the universe? Can you count the number? I mean, how many chemical reactions are happening in your body? That's a huge number of reactions. There's such a huge number, we try to classify these into categories. And we don't want to classify them into too many different categories. We want to classify them into broad categories. So we look at the chemical reactions. We're going to look at these later. Okay, when we're talking about mixtures and variable composition, the variable composition, we have different ways of describing the composition of it. And so oftentimes we'll say the percent composition M over M. Do you know what that is? Percent M over M is? Mass. And so this is mass of A over total mass times 100%. And so if this is A percent, then this is the mass of A over the total mass times 100%. And so we have percent composition, but we have a whole bunch of other ones that are similar to percent. So for example, percent is that, but we can have ppm. Have you heard of ppm before? What is ppm? Parts per, not milliliter, but parts per million. And so if I have a ppm, it's the same. It's the mass of A over the total mass, but rather than multiplying it by 100, we multiply it by 1,000,000 ppm. And so for a percent, we take the ratio and multiply it by 100. For ppm, we take the ratio and multiply it by 1,000,000. The units are different here. The units here would be percent, the units here would be ppm. Do you know what a part per billion is? A part per billion is going to be, rather than multiplying by 1,000,000, we'll multiply it by billion. So the reason we use parts per million is because if the percent, is out of range. So for example, if it's 0.001%, it's kind of small. And so rather than saying 0.001%, it might be more useful to say, it's 0.001 would be like 10 parts per million or 10,000 parts per billion. And so it's just at a different scale. But these are the two big ones, percent and ppm. In fact, you need to know this one for homework for chapter 1, the ppm. And the solution, we use ppm and ppb for dilute solution, and we use percent for more concentrated solutions. And we also have other ways, etc. And then we have things like molarity. Do you remember molarity? Molarity tells us the composition of a mixture in moles of A per liter of solution. This is molarity, etc. And so there are different ways of expressing the composition of a mixture. These are probably the three most, the most common. Molarity and percent are probably the most common. Percent for more concentrated. Density is just mass to volume. You should know some things, like the density of water. The density of water is about 1 gram per cubic centimeter. A cubic centimeter is the same thing as a milliliter, so it's 1 gram per milliliter. In fact, they're exactly the same. The density of wood, is wood more dense or less dense than water? Less dense. Would you say wood weighs half as much as water? A quarter as much? A tenth as much? It's like about half. It depends on the wood. Hardwood's a little higher, balsa wood lower. But, about half as much. Density of aluminum is about 3 times heavier than water. The density of aluminum is around 2.7 grams per milliliter. You might know this, the density of copper. This is an experiment. If you had Chem 4 here, you might know the density of copper. 8.9, does that sound right? About 9 times heavier than water. The density of gold. The density of gold is about a little less than 20. So we'll just say 20 grams per milliliter, 20 times heavier.
In this class, would you be expected to memorize anything like densities or specific heats?
Normally you're expected to memorize this. The reason you're expected to memorize some of these is this. Experiment A, I had a student, not just one student, I've had multiple students tell me that the density of water is over 400 grams per milliliter. So on experiment A, a student got the density of water, they calculated at 420, this is literally 420 grams per milliliter. But they had no idea. They had no idea how crazy that number is. Absolutely no idea that it's totally unreasonable. So this is just to help prevent you from making gross errors, because you might catch yourself, oh, that's impossible.
Oh, yeah, I get that, like a general feel for it.
I'm not going to ask you to, on a test, I'm not going to tell you, what is the density of gold of 3 sig figs? I'm not going to ask you that on the test. It's just to know ballpark range, that's it.
Okay.
we need to know some ballpark ranges. So let me ask you this: if I was hit by 1,000 nanometer light, do I start to stress out? If you're hit by 1,000 nanometer light, would you stress out? You probably never memorize this in Chem 4. But visible light has a wavelength range between what and what?
400, 800?
Yeah, about 400 to 800, or 390 to 760. You know what it is. So if you're at 1,000 nanometers, what type of light is that? It's infrared. So no big deal. I wouldn't worry about it so much. Unless it's a laser. Infrared lasers are very dangerous. If you're hit by light of 250 nanometers, would you worry about it? Yeah, I'd probably worry about it. I'd probably get sunscreen or something because that's ultraviolet light. And ultraviolet causes damage. And so there's certain numbers that you want to know, so that you have some. This is all ballpark stuff. Density of gases are about 1,000 times less. So rather than a gram per milliliter, let's just say 1 gram per liter would be 1,000 times less than. And then the most dense elements. What are the most dense elements? The most dense elements would be like osmium and iridium. And those just have slightly higher than 20. Those are the most dense elements. So those are densities. We use densities as conversion factors. We often calculate densities in problems. In fact, problem solving, this is a major topic of chapter 1. Although there's no section, so section 1 point all would be problem solving. Uncertainty in scientific measurements and sig figs. These we'll look at together. Uncertainty and sig figs. Whenever you take a measurement, there's always uncertainty. In fact, the only way you can get rid of that uncertainty is by definition. So, for example, 32 degrees Fahrenheit. If we measure that, then that's only 2 sig figs. Because is it right on 32, or a little bit above, or a little bit below? But by definition, that's where water is supposed to freeze. And so by definition, there's no uncertainty, but any measurement contains uncertainty. And so what we say is all measurements contain uncertainty. There's 2 types of uncertainty that we worry about in a measurement. What are the 2 types of uncertainty we worry about for measurements?
Validity?
I'm sorry?
Is it validity? For measuring, is it validity?
Fluidity? Yeah.
Validity.
Validity, actually, can you, my
I don't know.
my vernacular is not.
Is it valid or not?
Oh, okay. Is it valid or not? Yeah, a valid measurement, but what constitutes a valid measurement? For science, what constitutes a valid measurement changes.
What if it's precision?
Okay, precision, yeah. Okay, so we worry about the uncertainty because uncertainty is error. And so all measurements contain, 2 types of error, potentially. So all measurements contain error. And one of these errors is due to precision. Actually, let me get back to error. So I'm going to just talk about error right here. One of these is called, random error. Have you heard of that? Random error, this is kind of natural fluctuations. Now, when you look at the quantum theory, you cannot get rid of random error. You might have heard you remember Heisenberg? What was Heisenberg's principle? What was that? Heisenberg's blank principle. Uncertainty principle. What was he uncertain about? What was the error that he was worried about? Heisenberg. Well, Heisenberg, fundamentally, we cannot get rid of random error. There's always going to be these little fluctuations in this. So no matter how exacting that measurement is, there's going to be a theoretical limit to this. Unless you can take an infinite number of measurements. If it were possible to take an infinite number of measurements, then half the measurements would be reading kind of too low, and the other half would be too high. And therefore, if you average those together, you get the errors canceling each other out. And so random error can be minimized by taking more readings. The more readings you take, the better your average is going to be, the more accurate it will be. That's random error. And then we have something called systematic error. Systematic error, this in theory we can eliminate. This one is we can minimize but cannot eliminate. The way we eliminate systematic error is by calibration. You got to make sure the instrument is reading correctly. And so calibration can eliminate systematic. So systematic should not be a factor because all our measuring tools, measuring instruments should have been properly calibrated, therefore eliminating systematic error. So the only error we worry about is random error. And to minimize random error, we take lots of readings, and the more precise the readings are, the narrower we can make those. And the more precise, two things we want to do. One, we want to take more measurements. In science, oftentimes we don't just take one measurement. Oftentimes we'll repeat that measurement a minimum of how many times? Typically, the number is 3. Statistically, that's the biggest payoff.
Do you know what's rule under
Random error under random error?
Yes.
Can minimize. Can minimize but can't eliminate. So we minimize this by taking more measurements, and 2, we try to take more precise measurements. Precise measurements means using higher precision instruments to measure it. And so the more precision you can get, the more you can pinpoint. And so we have like rulers, like this, or yardstick. And then we have things called micrometers. Micrometers have these little clicking things and mechanical, and those you can get very precise measurements with. And those will narrow down the range. And so when we're thinking about errors, let's look at these two numbers, 5 grams versus 5.0 grams. Okay, then we look at 2 things here, accuracy and precision. So first, let's look at precision. Which of these 2 is more precise? This one's more precise. Do you see that? Because the rules of sig figs. The rules of sig figs tells us that the last digit that's written is the uncertain digit. So if this is the last digit written, then there's uncertainty in that digit. And so this means that this is anywhere from 4.5 to, let's say, 5.4 grams. Over here, the last digit written is this 1/10 of a gram. So if the 1/10 of a gram is uncertain, then this is going to range from 4.95 to 5.04 grams. And so this is a tighter range. It has higher precision. And so this is higher precision. Which one has higher accuracy? Well, we can't tell. We can't tell the accuracy. We can't tell the accuracy because the accuracy depends on if the balance was calibrated. If the balance wasn't calibrated, then neither might be very accurate. Or if the balance is calibrated, then usually the one with higher precision is in general more accurate, but not necessarily. And so these types of things we're thinking about, we'll talk more about these as we go along. And so we want to think in terms of measurement, we want to think in terms of accuracy, precision, we want to think in terms of random error, that is more measurements, more precise measurements, we can average those and get better results, and we want to think in terms of systematic error, make sure things are properly calibrated. But for right now, we're just going to play with the rules for sig figs and problem solving. Okay, so what types of things are we going to measure? Well, what types of things we measure are things like length. You know, what's the, do you know what the SI unit of length is?
Meter.
Is it the meter? Okay. We measure the length, which is in meters. This is the SI, the International System. How about, what else do we measure? Okay, volume is what we call a derived. Volume is the length times the width times the height. And so the volume would be meters cubed, which is a derived unit. So this is called a derived unit. But the base unit, this is the base unit here, it's just a meter. And we have area too. Area would also be derived, that would be meters squared. What else? Mass. What's the SI unit for mass? The SI unit is kilogram, but usually kilogram is too big. And so we use grams. Do you know the metric prefixes? Which metric prefixes should you know? You should know the big ones, like M. Capital N is mega. Mega is how much? A kilo is 1,000. Mega is a, yeah, 10 to the 6, a million. Sometimes we go bigger. Like a megagram, we'd never go. But a megahertz, we would. Or megabit, we would. What's bigger than a mega? Giga. Giga is 10 to the 9. So you could have a gigabyte. And then what's bigger than that? Tera. Do 10 to the 12. Then we need kilo. Everybody should know kilo. 10 to the 3rd. We need, what else? Centi. Centi is a little bit off because this is 10 squared. 100. And then let's go smaller. We need milli. Actually, this is supposed to be centi. Milli, which is 10 to the minus 3. And then what else? What's smaller than milli? Before nano. Micro. Micro gets the Greek symbol mu. And that is 10 to the minus 6. And then nano. 10 to the negative 9. And then there's a weird one that's stuck in here, the angstrom. The angstrom is only for length. It's not for anything else. And the angstrom is what? You might have heard this, you might not have. But the angstrom, A-N-G-S-T-R-O-M, is 10 to the minus 10 meters. You know, what's significant about an angstrom? Size of the atom, right? Atoms are like 1 to 6 angstroms or so. in diameter, and so it's useful for that. Nano, and then what's smaller than nano? Pico, 10 to the minus 12, and then femto. That's probably all we need. 10 to the minus 15. Femtosecond. Chemical reactions happen at that speed. Some chemical reactions happen in a femtosecond. So this is why when people are interested. Picosecond is too slow. So if you try to catch a chemical reaction in a picosecond, it's too late. You've missed it. It's like the collision's happening. And so people are using femtosecond lasers to pulse really fast so they can see the reaction happening in real time. Rather than the reactants in the products. They want to see bonds breaking and bonds forming. So that's why people are interested in this kind of stuff. So one of the things I recommend that people do for studying is to get the complete solutions guide. You know, when I was a student at UCLA, one of my classmates, actually it was my first quarter at UCLA. And I went through the whole orientation thing, chance for orientation, this. They said, oh, your first quarter, your GPA is going to drop by 1 unit minimum. And I thought, okay, now I'm prepared for that. And so I'm not going to let that happen to me. I'm going to make sure I stay on top of it. And so I did, and then the first class I took at UCLA in Chem was this physical chemistry, P-Chem they call it. It's a mix of physics and chemistry. And in P-Chem, it's notoriously a difficult class. They have bumper stickers that they sell. And somebody bought me this. I never bought it for myself, but there's a bumper that says, I passed P-Chem. And so I have it. It's sitting around. I never put it on my car, though. I feel embarrassing. But I barely didn't pass P-Chem. The first test I had, I didn't do very well. Why? I studied. All I did was study, because I didn't want my GPA to drop. And so the person sitting next to me got the high score on the test. So I started asking him how he studied. And one of the things he did was he did all the problems in the chapter. And I thought, how could you do all the problems? I mean, doing one problem takes me an hour. There's no way I can do all of them. And the way he did all of them is he had the complete solutions guide. So you read the problem, read the answer, read the problem, read the answer. Didn't spend that much time.
In the blanks.
Yeah, and then you thought, that's not a lot of instructors hate that because they think, that's not learning, that's memorizing, But in a way, it is learning because once you get all the basics down, then the advanced learning comes by interweaving all the basic concepts to do advanced problems. Advanced problems are just interweaved basic problems. But anyway, that's something I started to try to do. If there's a complete solutions manual, then I did it. And the reason is when you're starting off in a new field, you don't have 30 years of experience doing chemistry problems, do you? What you need to do is you need to get yourself up to speed quickly. How do you get yourself up to speed quickly is not by spending all your time working on one problem. If you're spending, let's say on one problem I was spending 2 hours. If you're spending 2 hours on one problem, then you're missing the forest. It's like you're in this forest up in the Sierra. And all you're doing is you're looking at one tree. And what did you do over the summer? I spent my time in the forest in the Sierra studying the forest. I just looked at one tree the entire time. Are you going to learn much? No. And so what you need to do is you need to, even if it means you don't know that tree as well, you need to see the whole forest. And in order to see the whole forest, you got to expose yourself to a lot of different problems. And then once you see all these variations, then this is like, driving. following the directions or walking, along a path. You walk the same path, eventually you have that path memorized. And then once you have that path memorized, then you can look at all the branches. Oh, I didn't see that road going down that way. There looks like to be some interesting stuff over there, right? And then when you get to that level, then you can start thinking about how these things are intertwined with one another and how these concepts. So a lot of people will say, oh, that question was nothing like the test, but in reality that question was, nothing like the homework. In reality that question was just like the homework, but it was just looking at it in a different way. And so these are some of the things. So let's take a look, and this is what I want to do here, is I want to take a look at the problems. And we're going to, since a lot of this is review, I'm going to skip all the other stuff. We're just going to go to the more advanced problems here. So let's take a look at looking at some of these problems here, like number 67. According to the rules of significant figures, the product of the measured quantities, 99.9, how many sig figs? 3. And 1.008, how many sig figs? 4. So if you multiply those together, how many sig figs are you allowed in the answer? 3. And so the product should be expressed as 3 significant figures, 101 square meters. Yet in this case, it worked to be more appropriate to express the result of 4 significant figures, 100.7 square meters. Explain why.
My explanation would be that both of our measured quantities go past the decimal point, while our answer wouldn't. So it would be more accurate to go 1 decimal place after.
Yeah, that's basically it. This is a more accurate representation of uncertainty in this calculation. In fact, sig figs are simplification of the way we do. If you have calculus, then the way we handle uncertainty in measurements is not with sig figs and the rules for sig figs. The rules for sig figs are a simplification of something called propagation of errors. But in order to do propagation of errors, I actually don't need calculus. It's a lot easier if you have calculus. What we do is we look at the percent error in these. And then we say, okay, if the percent error is this and the percent error is this, then our final answer should have roughly the same percent error. And so this would be it. And so the sig fig rules are simplification of the propagation of errors, which would be a more accurate way of representing uncertainty. If you were to follow the rules, which we do, we get this, 3 sig figs, but that's not the best. This would be better. Rules are not like laws, There's a distinction between rules and laws. Laws are not really meant to be broken, Whereas rules, you can break rules. Rules can be broken, and they often are. Although, a lot of laws don't work. They're modifications to laws, like the ideal gas law. What do you do for real gas? '68. So we try to go through these without. Obviously, the best is just to figure it out yourself without having to look at the solutions manual. But you don't want to spend too much time, especially if you have a lot of problems. So 68, for a solution containing 6.38% para-dichlorobenzene by mass in benzene, the density of the solution as a function of temperature in the temperature range 15 to 65 degrees C is given by the equation. This is called an empirical equation. So they just look at how the density of this mixture varies with temperature and then come up with a graph and then come up with an equation for the graph. And so this is the mathematical equation. It doesn't come from theory, it just comes from observation. So these empirical equations are very common. So this would be the law of the density of this mixture. At what temperature will the solution have a density of 1.543 grams per milliliter? So, this is just algebra. So we plug in 1.543 grams per milliliter here and then solve for T. Does that make sense? And so I just look, that's just algebra. I'd look in the solutions manual and see, is that just basically it, or am I missing something? I don't know why this is advanced. It's advanced because of this equation, probably. You haven't seen an equation like this. And so I have the solutions guide here. Let me see if I can make this thing work here. And so what you just do is just confirm it. Looking at the solutions guide, is that how they actually did it? Let's see if this works. Was it 68? I hope I didn't do something bad. That is, I'm not. Oh, there. Okay. Bad meaning. Sorry, I'll need more time to figure this one out. Yeah, so I look at it, yeah, basically it's just algebra, so it's not. But the empirical equation could throw people off. Hey, I've never seen that equation before. The instructor never talked about this equation, right? Why are they throwing this equation on here? And so that's probably why this is in the advanced section. Otherwise, I can't think of the reason why. Okay, let's go to the next page. All right, the most common technique that we use in chemistry to solve problems is dimensional analysis. Just using conversion factors. All of you are familiar with it, pretty much? Yeah. Some of the advanced problems involve multiple unknowns. And so number 69 is a problem that involves multiple unknowns here using dimensional analysis. So let's take a look at number 69 here. A solution used to chlorinate a home swimming pool contains 7% chlorine by mass. An ideal chlorine level for the pool is 1 part per million. Think of 1 ppm as being 1 gram of chlorine per million grams of water. If you assume densities of 1.10 grams per milliliter for the chlorine solution and 1.00 grams per milliliter for the swimming pool water, what volume of the chlorine solution in liters is required to produce a chlorine level of 1 ppm in an 18,000 gallon swimming pool? So there's a lot of stuff in this problem. So what we normally do is we try to break it down into conversion factors and given units and this kind of stuff. So so the first thing is a solution used to chlorinate a home swimming pool. So this is the chlorinating solution. So what do we know? Well, we know that this solution is a mixture that contains 7% chlorine by mass. And so 7% means 7 parts per 100. So 7 grams of chlorine per 100 grams of chlorine solution, or chlorinating solution, which is a mixture. All solutions are mixtures. Solutions are homogeneous mixtures. And so this would be the first conversion factor that we get from this. An ideal chlorine level for the pool is 1 part per million. So for the pool, we want 1 gram of chlorine per million grams of pool water. If you assume densities of 1.10 grams per milliliter for the chlorine solution. So the chlorinating solution is going to have a density of 1.10 grams per milliliter. Now, what we have to do in Chem 1A versus Chem 4 is we have to be more descriptive. And so we'd never leave it like this in Chem 1A. Instead, we'd say 1.10 grams of what? Chlorine? No, this is going to be chlorine solution. So we'll write chlorine solution, good. Per milliliter of what? Per milliliter of chlorine solution is the same. So that's the density of gold is 20 grams of gold per milliliter of gold. Okay, and then the density of the pool water is 1.0. If you see a density of pool water of 1.0 grams per milliliter, that means it's nearly pure water. Nearly, would you drink it though? Probably wouldn't drink it, but it's close to pure. It's got the density very close to pure water. Pure water is slightly less. Get to 3 sig figs. This is the 3 sig figs. And so this is going to be grams of pool water per milliliter of pool water. Okay, then we have 18,000 gallon swimming pool. So what we try to do sometimes is we try to visualize what's happening here. And so I have an 18,000 gallon swimming pool. And what I'm going to do is I'm going to pour some chlorinating solution in here. And what they're asking for is how many liters of chlorinating solution do I need to pour in here? And so the question is how many liters of this chlorinating solution do I need to pour in here to get the ideal level of 1 ppm chlorine? In this swimming pool. So how can I solve this? Well, the way we solve most problems in chemistry is by dimensional analysis. We're going to start off with a given. And so what do we know that's fixed, that we can't change? Well, these are what we call extensive or intensive properties. Do you know the difference between an extensive property and an intensive property? Okay, these are examples of intensive properties. For example, does the 7% depend on how many gallons of chlorinating solution I have? So for example, if I had 1 gallon of 7% chlorinating solution, if I had 2 gallons of chlorinating solution, would it be 14%? Or would it still be 7%? It would still be 7%. If you bought 2 gallons of milk versus 1 gallon, is 2 gallons of milk twice as concentrated? Or does it taste the same? Does it taste the same as 1 gallon of milk? Yeah, it tastes the same if you drink them, that is, or whatever. Those are intensive. Intensive doesn't depend on the amount. So if I bought a gallon of chlorinating solution, it's this. If I bought 10 gallons of chlorinating solution, it's still this. It's still the same, 7%. Does that make sense? Density, is density intensive or extensive? So if I have a gallon, it's 1.1. If I had 2 gallons, is it 2.2, twice as dense? No, it's the same. That's intensive, independent of the amount. Intensive means independent of the amount. How about the 1 ppm? Does that depend on how big the swimming pool is, or we want 1 ppm regardless of what the size of the swimming pool is? We want 1 ppm regardless of the size, right? That's intensive, independent of the amount. How about 18,000 gallons of pool water? Is that intensive or extensive? The volume of the swimming pool is extensive. The volume depends on the amount. So what else is extensive? Mass. How much something weighs depends on how much. The density? No. The mass? Yes. The volume? Yes. Extensive. And so, this is it. So our given is this. This is our given. We're given an 18,000 gallon swimming pool. And so normally that's where we start off with. We start off with 18,000 gallons of swimming pool water. And that's our, what we call the starting point for this. But there are actually two unknowns here. The two unknowns is it still going to be 18,000? We're going to be dumping some chlorinating solution in here. When we dump the chlorinating solution in here, doesn't that change the volume? So the volume of the swimming pool is actually a little bit bigger. It's going to be 18,000 gallons plus the volume of the chlorinating solution. We dump in there. Well, how much chlorinating solution are we dumping in there? Do we know how much? We don't know how much.
How can you determine in the board problem whether it's intended that the 18,000 gallons is the solvent or the solution? Because here it acts as a solvent, but how would you differentiate what they want?
Because the solvent would be the major component, but you got to be careful because this is called the chlorinating solution. Both are solutions.
Oh yeah.
The pool water is a solution, and the chlorinating water is a solution. So the pool water still may not be pure, but it would be the solvent because we're dumping in the chlorine into there. So this is like a solution-solution type problem. And so I hope that answered it, but if not.
Okay, thank you.
So the first unknown is we don't know how much, because the greater the volume of the swimming pool, the more chlorinating solution we have to put in there. But then we don't know how much chlorinating solution we're putting in there. You see that? And so there are two unknowns. And so the volume of the swimming pool and the volume of the chlorinating solution are our two unknowns. In a typical dimensional analysis problem, we just are searching for one unknown. That is what our desired quantity is. And so we have two desired quantities here. So there's given and desired. The desired quantity, chlorinating solution, and the swimming pool. So when we have two unknowns, what do we have to do? What do you do when x and y? Let's call one of these x, the other y. If we have x and y, both are unknown, we need... I'm sorry? Yeah, so what you typically do, you solve for one variable and you substitute. In other words, you do two equations and two unknowns. So what are the two equations? Well, this is the first equation. What's the other equation? The other equation is going to come from dimensional analysis. So this is actually, we're starting off with a pretty tough problem here. But this is still chapter 1 of our book. And so the other problem is, if we know the volume, so what we want to do is we want to figure out the volume of the chlorinating solution in liters. What are we given? Well, we need to know how big the swimming pool is. And so we need the volume of the swimming pool. We have the volume of the swimming pool in gallons. here. Okay, so in dimensional analysis, what we want to do is we want to cancel out gallons or gallons of pool water. Okay, when I look at the things I erased, was there anything that had gallons of pool water in there? No, so we can't use gallons of pool water, so we're going to use gallons. And so what I'm going to do is I'm going to go gallons to what? Liters. And so this is a conversion factor that you may or may not know. It's 3.785 liters in a gallon. This is to 4 sig figs. Here. So 3.785 liters to gallon. So now we have liters of pool water. And we want to cancel that out. Is there something that cancels out liters or liters of pool water? There's nothing that has liters of pool water. There is something that has milliliters of pool water. So if we go from liters to milliliters, that will help. And so this one is this. How many sig figs in this conversion factor? Here. Infinite sig figs. Now, something that's a bit tricky here is in the numerator I have 4 sig figs. In the denominator, how many sig figs do I have? 1. In the denominator, I have infinite sig figs. This is the way we read this conversion factor. In exactly 1 gallon, there's approximately 3.785 liters. And that way, we don't want to say this. We don't want to say in approximately 1 gallon, there's approximately. We don't want approximate. We keep one exact and throw the uncertainty in the other term. And so over here, in exactly 1 liter, there's exactly 1,000 milliliters. This is by definition. Okay, so now the gallons cancel. We don't know how many gallons we have here because we're adding some chlorinating solution. The liters cancel, and now I have milliliters or milliliters of pool water. Well, I can get rid of milliliters of pool water. And so I'm going to use milliliters of pool water. What will get rid of milliliters of pool water? I have 1.00 grams of pool water per milliliter of pool water. Okay, so I don't know exactly where I'm going, but we just keep going until we either come to a dead end or the answer. And so is this persistent? Here, we don't have too many branches we can go. There aren't that many paths. And so either I'm going to get rid of grams and convert it to pounds, milligrams, whatever, or grams of pool water. Do I have something that gets rid of grams of pool water? What? Yeah, we have 1 gram of chlorine per 1 million grams of pool water. And so I can get rid of grams of pool water. And so grams of pool water cancels out grams of pool water, and that leaves me with grams of pure chlorine. Now I'm going to try to get rid of grams or grams of pure chlorine. Do I have something that gets rid of grams of chlorine? And what is it? 7 grams of chlorine per 100 grams of chlorinating solution. Okay, then I need to get rid of grams or grams of chlorinating solution. So is there something that gets rid of grams of chlorinating solution? Yeah, what is it? 1.10 grams of chlorinating solution per milliliter of chlorinating solution. Okay, and then I need to get rid of milliliters or milliliters of chlorinating solution. In this case, I could use milliliters of chlorinating solution, but that's going to take me in a circle because that will take me back to grams. And so what I'm going to do is I'm just going to get rid of milliliters and convert it to liters. And so 1,000 milliliters per liter. And that leaves me with liters of chlorinating solution. Well, that's what we wanted. We wanted liters of chlorinating solution. However, I have one problem. I don't know what the volume is because figuring out the final volume of the pool depends on how much chlorinating solution I add in there. The more chlorinating solution, the little bit more I have to add. And so here I'm going to have the equation 1. This is equation 2. And I'm going to do a substitution here. So from equation 1, I'm going to get the volume of the swimming pool is equal to 18,000 gallons plus the volume of the chlorinating solution. Well, the volume of the chlorinating solution is in liters. And so this is chlorinating solution in liters. And what I'm going to do is I'm going to change that to gallons by just using this conversion factor. 1 gallon is equivalent to 3.785 liters. Okay, so I'm going to have gallons plus gallons. And so it depends on how many gallons of chlorinating. The more gallons of chlorinating solution I add, the more volume I'm going to have to chlorinate overall. And so I'm going to substitute this, and I'm going to call this X, and solve for X here. That is, this is X, and so what I'm going to do is I'm going to X is equal to 18,000 plus X. Then I'm going to just use the numbers. The units all work out, so it's going to be times 3.785 times 1,000 times 1, I'll skip that, divided by a million times 100 divided by 7 divided by 1.1 divided by 1,000. Then solve for X. Once we have X, then that gives us the volume of chlorinating solution in liters. And then once we get the volume of chlorinating solution, we can convert that to gallons and figure out what the final volume of the swimming pool is. It's going to be more than 18,000 gallons. Does that make sense? I did this in Chem 4, but what I did in Chem 4 was a very common thing we do in science. A very common thing we do in science is we make simplifying assumptions. One of the simplifying assumptions that we make is this. You know, do you expect how many gallons of chlorinating solution am I going to have to add in the swimming pool? 10 gallons? 30 gallons? 50 gallons? If I had to add 50 gallons of chlorinating solution to the swimming pool, that's a lot of gallons. But what if it were like 1/10 of a gallon? If I only had to add about 1/10 of a gallon, is that much? Do you think 1/10 of a gallon of chlorinating solution is going to change the volume of the swimming pool by much? No. And so in science, what we often do is we say, I don't want to do two equations and 2 unknowns. I just want to do 1 equation with 1 unknown. And so oftentimes in science, we make a simplifying assumption. We say, you know what? I'm going to assume I'm barely going to add any of this. If I barely add any of this, then it's not going to change the final volume by much. Yes, it's going to be an error, but the error is going to be very small. And so what we do is we assume that this is negligible. If this is negligible, then we know what the volume of the swimming pool is. It's going to be about 18,000 gallons. Is that correct? No, it's going to be a little greater, but it's not going to yield that big of an error. So it looks like I'm out of time here. So actually, we'll just continue. We'll continue tomorrow.